Have you ever picked up a bottle that says something like 10% solution and just kind of wondered, what does that actually mean? It sounds super simple, right? But in the world of chemistry, figuring out how much stuff is dissolved in a liquid, well, it can be measured in a few different ways. And trust me, those differences are really, really important. So today, we're going to demystify all these concentration terms.
Yeah, exactly. Does it mean 10 grams of something in 100 grams of liquid, or is it maybe 10 milliliters of stuff in 100 milliliters of liquid? It seems like such a tiny detail, but as you're about to see, it can have some pretty huge consequences. So let's break it all down.
All right, before we get into the weeds, let's cover the absolute basics, real quick. So every solution has two main parts. First, you've got the solute. That's the stuff that's actually being dissolved. Think sugar in your coffee. Then you have the solvent, which is the thing doing the dissolving, so the coffee itself. You mix them together and boom, you've got your solution. Simple enough, right? This is the foundation for, well, everything else we're going to talk about.
Okay, so our first method is what's known as weight by weight, or as you'll see it written, %W/W. Now pay attention to that subtitle, the temperature proof method. That is a massive clue right there. I want you to just kind of keep that thought in the back of your mind, because it is basically the key to this whole puzzle.
So here's the formula, and it's pretty straightforward. It's really just asking a simple question. What percentage of the solution's total weight is actually the solute? We're comparing the same units, mass to mass or grams to grams. It's a true apples-to-apples comparison. You just take the weight of your solute, divide it by the total weight of the entire solution, and then multiply by 100 to get your percentage. That's it, a pure mass-to-mass ratio.
Okay, let's put this into practice with an example. Let's say we've got 9 grams of a solute. We'll use urea here, and it's dissolved in a solution that has a total weight of 90 grams. So what's the percent weight by weight concentration here? Think you can figure it out?
Well, we just plug the numbers into our formula. You take 9 grams divided by the total of 90 grams, that gives you 0.1. Multiply that by 100, and there you have it, 10%. So this is officially a 10% weight by weight solution. And what that really means is that if you had 100 grams of this stuff, exactly 10 of those grams would be the urea.
All right, so that was weight to weight. Pretty logical, right? But what happens when we start mixing our measurements? What if we measure the solute by its weight, but the whole solution by how much space it takes up? Well, that brings us to our second term, weight by volume, or %WV. And yeah, as you can see, we're literally mixing mass and space here.
You see the shift in the formula here? The top part, the numerator, is exactly the same, the weight of the solute in grams. But look at the bottom, the denominator. That's changed. Instead of the solution's weight, we're now using its volume, measured in milliliters. This is a really crucial difference. We're no longer comparing apples to apples. We're comparing grams to milliliters, mass to space.
Okay, let's try an example for this one. Imagine we have 8 grams of sulfuric acid, which is H2SO4, a really common chemical. And it's dissolved in a solution that fills a beaker up to the 80 milliliter mark. So, what's the percent weight by volume? Again, the math's pretty easy, right? 8 divided by 80 times 100, that gives us 10%. So wait a minute, it's another 10% solution just like the first one. But, and this is the really critical part, this is a 10% weight by volume solution. On the label, they might look identical, but because this one involves volume, it behaves in a fundamentally different way, and we're getting very close to why.
Okay, so we've done weight to weight and weight to volume. So what's the last logical step? Well, of course, it's volume by volume, or %V/V. This is the one you see all the time when you're mixing two liquids together. The classic example is mixing something like alcohol with water.
And honestly, this one is probably the most intuitive of them all. You're just comparing the volume of the thing you're dissolving to the total volume of the final solution. Everything's in milliliters. It's just a straight-up volume-to-volume ratio. So let's do a quick example. Let's say we mix 25 milliliters of ethanol, the alcohol in alcoholic drinks, and our final solution has a total volume of 50 milliliters. What's our percent volume by volume?
You can probably do this one in your head, right? 25 divided by 50 is 0.5, or 1/2. Multiply by 100, and you get a 50% volume by volume solution. And yeah, that would be a very, very strong mixed drink.
Okay, let's stop for a second. We've just looked at 3 totally different ways to calculate a percentage for a solution. And that leads to the big question. Why? Why do we even need 3 different methods? It all comes down to one single crucial factor: temperature.
Yep, this is what it's all been leading up to. Remember, way back at the beginning, I told you to remember that weight by weight was temperature-proof? Well, now we're going to find out exactly why that's not just some catchy phrase, but an absolutely critical scientific property.
So let's just think about a basic rule of physics for a second. If you have, say, a chunk of metal, its weight, its mass, is the same whether it's sitting in a freezer or glowing red hot, right? The amount of stuff it's made of doesn't change with heat. Mass is constant.
But its volume, that is a whole different story. You heat up that same chunk of metal and it will actually get a little bigger. It expands. You cool it down, it shrinks, it contracts. And the exact same thing happens with liquids. Volume is totally at the mercy of temperature.
And this is where it all comes together. Take a look at this table. Since percent weight by weight only deals with weight, which doesn't change with heat, it is completely independent of temperature. But the other two, weight by volume and volume by volume, they both have volume in the equation. And because volume changes with temperature, any measurement that uses it is automatically dependent on temperature.
So here is the absolute bottom line, the most important takeaway. If you see volume anywhere in the calculation, you know that temperature can change your result. That 10% weight by volume solution you carefully prepared in a cool lab, on a really hot day, the liquid might expand, and suddenly it's actually a 9.9% solution. And in science or medicine, that tiny difference can be absolutely huge.
Okay, let's do a super quick recap. What are the big things to take away from this? 1. Concentration is just a fancy way of saying how much stuff is in a solution. 2. Percent weight by weight is your rock. It's stable and doesn't care about the temperature. 3. Anytime volume is involved, so percent W by V or V by V, your measurement is going to change if the temperature changes. And that brings us to the final point. For any kind of precision work, you absolutely have to know which type of concentration you're dealing with.
And this is why this isn't just some boring textbook detail, you know? Think about a pharmacist preparing a liquid medication. If the concentration is off by just a tiny bit because the pharmacy got too warm one afternoon, the dose could actually be wrong. In any kind of scientific work, precision is everything, and that means you have to account for variables like temperature.
So, there you have it. That little percent sign on a label, it's hiding a much bigger story. So the next time you see it, you'll be one of the few people who knows to ask the real question. Is that by weight or is that by volume? Because now you know just how much that difference can matter.